In this video, we'll talk about exponential models. First, the vocabulary. When we deal with exponential regression, this is the method of fitting an exponential function to a set of data. Our half-life is the time it takes a quantity to decay to half its original amount. It usually applies to exponential decay equations. Example 1. A tour guide noticed that larger groups took more time to assemble for an event. The guide collected the data below. We want to make a scatter plot, find a linear regression model and graph it, and find the exponential regression model and graph that as well. Then we'll say which of the two models seem to fit the data better and explain why. So to solve this problem, we use Desmos. So in Desmos, what we want to do is first add a table. And we're going to enter the number of people into X1. Four, 5, 6, 7, 8, 9, 10. And enter the time to assemble 2.6 minutes, 3.4, 4.4, 5.7. We can see our scatter plot starting to come in, 7.4, 9.7, 12.5, and 16.3. And we can hit our magnifying glass and get a clearer view of our scatter plot. Okay, so the first piece wants us to find a linear regression model and graph it. So that will be y1, hit the tilde. The tilde is under the keyboard. Then we want mx1 plus b. So as we can see, the line doesn't hit that many of the points. And we have our value of 96. So that's a strong fit. And our R squared value is 0.92. So that's saying that 92% of the data fits the model. Now let's try the exponential model. So that'd be y1, and then hit the tilde. A, and we can actually just use parentheses. Parentheses B, and then hit the exponent, x1. And we can see with the exponential model already, we have a much better fit. Let's hide the linear model. The exponential model is a much stronger fit. Like almost every point hits this line. Our R squared value is 1, which tells us that 100% of these points hit the line. So we've already made our scatter plots from Desmos. We're just going to write down our equations and answer the question. So for B, the linear regression equation was y equals 1.71 x minus 3.14. For C, the exponential model is y equals 1.19 parentheses 1.30 the x, and the stronger model is the exponential. The exponential model is better. Since r squared equals 1, which means 100% of the data fits the model. And we are done. Example 2. Brandon bought a new car for $30,000. It wasn't until he drove away that his friend Kyle mentioned that the car is going to depreciate at a rate of 50% per year. The value for calculating decay is again very similar to VF equals VI times R to the T, where VF is the final value and VI is initial value. R is the decay factor or depreciation rate, and T is the time in years. What is the decay factor of the car? So since we're decaying, it'll be just, first we do 50 divide 100, which gives me 0.50. Now we just do 1 minus 50 equals 0.50. So that's my decay factor. Part B, how much will the car be worth in 5 years? So in 5 years, we have to first write our equation. So it'll be VF equals 30,000. And I calculated you want to put the comma in, so I'm not going to erase that comma. So you know, don't put that comma in when you put in the calculator. Times 0.50 raised to a t, that's your function. So now you're just going to plug in 5. So 30,000 times 0.50, and 50% does seem to be a very high depreciation rate, but that's what this problem is asking for. Just keep in mind when you do buy a car, it does lose quite a bit of value within every time. So 30,000 parentheses 0.50 raised to 5, and this car, based on a 50% depreciation rate, is worth $937.50 in 5 years. So we'll just say worth $937.50 in 5 years, and we are done. Example 3. Carbon-14 has a half-life of 5,730 years. You're presented with a document which purports to contain the recollections of a Mycenaean soldier during the Trojan War. The city of Troy was finally destroyed in about 1250 BC, or about 3,250 years ago. Carbon dating evaluates the value ratio of radioactive carbon 14 to stable carbon 12. Given the amount of carbon 12 contained, a measured sample cut from the document, there would have been about 1.3 times 10 to the negative 12 grams of carbon 14 in the sample when the parchment was new. Assuming the proposed age is correct, according to your equipment, there remains 1.0 times 10 to the negative 12 grams. Is there a possibility that this is a genuine document, or is this a recent forgery? Justify your conclusion. So first thing we want to do is finish filling out the table. So at 0 years, we have 1.3 times 10 to the negative 12. Then the first half-life will be 5,730. Let's fill that in first. The next one will be adding 5,740 to itself. And that would give me 11,460. The second half-life will be adding 5,740 to 11,460, and that will give me 17,190. Now, to get the bottom line, what we need to do is we need to do half of each of these initial value. So first we enter in the calculator 1.3 times 10 up to the negative 12. And in the calculator, E means 10 times 10 to some power x. So we're going to do half of that, so times 0.5, and we get 6.5 times 10 to the negative 13th, or e to the negative 13th. Then we do half of that value, and we get 3.25 times 10 to the negative 13th. And one more time, times 0.5, and we get 1.625 times 10 to the negative 13th. So part B is asking for an exponential model for the amount of carbon 14 left as a function of time. So I'm going to say f of t equals 1.3, which is my initial value, times 10 to the negative 12 times 1 half t divided by 5,730. And this is an exponent. So for part C, we want to determine if this is a genuine document. So what we're going to do is we're going to use a Desmos, and we'll just say 1.0 times 10 to the negative 12 is our one function, and we'll set that equal to 1.3 times 10 to the negative 12 times 1 half times t to the 5,730. We'll set these two equal and determine what the t value equals. So we're looking for what the t value equals, or where do they intersect. Okay, switching over to Desmos. Okay, to solve this in Desmos, first thing you want to do is you want to say y equals 1.0 times 10 raised to the negative 12. Okay, we see a line, but we can't quite make out what it is. We'll fix our window after we enter our next equation. The next equation we want to enter is y equals 1.3 times 10 raised to the negative 12 parentheses 1 half, close your parentheses, hit your AB, then your exponent, x divided by 5,730. So instead of using 2, we're going to use x. Okay, next step, we're going to fix our window. So we'll hit the wrench. First, we'll turn on projector mode to makes it a little easier to read. And for our x-axis, we're going to go from 0 to, let's say, 5,730. So it hasn't been 5,730 years since the age of this document. And then for our y window, we know it started at 1.3 times 10 to the negative 12. So we can get from 0 times 1.3 times 10 raised to the negative 12. And now we can see our point of intersection. So we're going to find it. So to find our point of intersection, we'll click on the graph and we'll approximate where it is. So if I click on the purple line, which is the 1.3 times 10 to the negative 2, that is the decay equation. We just drag it until we get close to that green line. And get a little bit closer. It looks like it's about 2,170 years old. Somewhere between 2,166 and 2,170 years old. So let's answer our question now. So we say the document is approximately 2,166 to 2,170 years old. So this is a hoax. It's a fake because Trojan War was 3,250 years ago. And we're done answering the question.